All right, this is your final lesson in our quadratic unit about systems of inequalities. A few things you need to remember with systems of inequalities and graphing. When do you have solid lines versus when do you have dashed lines? Something you're also going to need to remember is when do you shade above a line and when do you shade below a line, okay? Same strategies will apply here. When I'm given this first system here, I'm just going to graph both individual inequalities and just treat them like they normally are. So for example, I'm first going to just deal with x squared minus 2. That's just a normal parabola, but he gets shifted down 2 units, okay? So if I go to graph him, vertex got shifted down 2 units, and now he's located at 0, 2. And I can use that step method to graph it, where I went up 1 and over 1, and then from that next point went up 3 and then over 1. And so this will take the shape of my parabola here, okay? Because my first example is a greater than, and it's not an or equal to, I must actually create the dashed lines, okay? All right, so now something to recognize is for him, I would be shading above the line, okay? Keep that in mind. But when it's a system, it must satisfy both inequalities. The next thing I need to worry about is my next equation. So to help me graph him, I'm actually going to find my axis of symmetry. So my b value for my next one is -3, and my a value is -1. So this gives me my axis of symmetry at -3/2. And if we plug in -3/2 into our equation, we're going to get a y value of 6.25. If you're preferring decimals, just remember that -3/2 is really just -1.5. So if I go to plot these, it's approximately right here. I'm trying to do my best with precision. Another thing to recognize is the fact that our c value is 4, which tells me I also have a coordinate at 0, 4, because he is our y-intercept. So I can also plot him, and I can use symmetry because 0 is 1.5 units away from our axis of symmetry, and in the other direction it'd be -3. So -3 and 0 are actually going to share the exact same y value, okay? To create a little bit more precision, and I don't want to just stop graphing this, and there's the start to it, why don't we also plug in a x value of 1, okay? So I'll give you a second. Plug in an x value of 1. Remember to follow order of operations when doing so, and you should get a y value of 0. I can now plot that there. Keep drawing my parabola. Okay, and that means right there. All right, so now where are we going to shade? So we already recognize that our parabola that opens up, we're shading inside of him because that's where it's above the line. Now my blue parabola was a less than. Less than means I need to shade below him. So where I'm below the blue line as well as above my upward one is this shaded region right here, okay? So in these notes that were provided by a text, it was also just a fill in the blank. And so the blanks here are where it's inside and inside, because that's where we just so happen in this example to shade. Both of them were inside the parabolas. Now sometimes you will shade on the outside, and it's just dependent. That's why I don't really say inside or outside. I just think of it as above or below the line. All right, last example here, and so it's called a checkpoint in the textbook, but we're just going to treat it as another example for us to play around with. So if we graph each individually, the first one is -x squared plus 3. That's a parabola that's going to open down that got shifted up 3 units, okay? He's going to be a dashed line because we're not or equal to, and because I'm less than, I'm going to shade below his lines, which once again it happens to be on the inside of the parabola. All right, so let's tackle this one and take care of it. So we have gotten shifted up 3 units, which is why we have a y-intercept of +3. And because our a value is 1, we're still going to follow this logic of typical step patterns of parabolas. So we went up 1 and over 1, and then from that point we went up or down, well, we're going down in this case, down 3 and over 1. So now what about the next one? We are going to first find his axis of symmetry because that's going to help us out. So our b value is 3 and our a value here is 2. So we have an axis of symmetry at -3/4. Take a moment, plug in -3/4 into your function, and when you plug in -3/4, you should receive a y value of negative 3.125. So if I go to kind of accurately, it's not going to be super accurately plot him, it's about right there. Another point we know for sure that we have is a y-intercept of negative 2, okay? So we're going to use some symmetry here, and if we're 0.75 units away from the 0 line, we're going to go 0.75 units the other direction, which is about 1.5. And if we start to connect our dots, it'll start to take the shape of our parabola here, okay? Notice I haven't done any of my dashed lines yet or my shading. Let's also plug in a value of 1 to get a little more precision here. So 2, 1 squared plus 3 times 1 minus 2. So this is going to get us 3. So that's up here. And we shoot up like this and shoot up right there. All right, so my very first equation, my black line, actually is going to be a dashed line. So I'm going to erase some of my lines here. And now I need to figure out where I'm shading. The black line, I'm less than, so I am below the black line. And the blue parabola, I'm greater than, so I'm above him. And once again, I'm creating this region in between, but once again, I'm going to warn you, it's not always going to be the in-between value. So it's actually in your best interest to pick some tester points maybe, or just consistently follow the above the line or below the line. If you're picking the tester point method, if the tester point works in both of your inequalities, then it is a solution to your system, so it lies in the shaded region.